Hello and welcome. In this video, I'm going to examine the 8051 Program Status Word, Psw Register. I first examined the Psw Register in one of my previous video, that is video 31, when I looked at the 8051 stack. And in this video, I'm going to revisit the 8051 Psw Register in more detail. So, introduction. Let's take a look at the EdSim51 and let's locate the Psw Register, and it's here. It's located here. So what I'm going to do is I'm going to extract this part here. It's a bit blurrish, but just hold on for a while. I'm going to redraw this in a moment. So the Psw Base Register basically shows the status of the operation that is carried out in the 8051. Yep, as mentioned earlier, I've redraw the Psw here. Basically, the Psw register is an 8-bit register. Only 6 are used by the 8051. These are CY, AC, RS1, RS0, 0V, and P. F0 is for user application, and this bit here is what we call the reserve bit. So let's take a closer look. So CY is the carry flag, AC is the auxiliary carry flag, F0, that's the flag 0. As mentioned earlier, this is for user application. And these two bits, RS1 and RS0, they are used for register bank select. In my previous video, that is video 31, when I talked about the stack, I mistakenly labeled this as RS2. This is the correct label, RS0. All right, I would like to just clarify that. And then this is the 0V flag, the overflow flag. As mentioned earlier, this is the reserve bit here, not used at all. And finally, but not least, this is the parity flag. Okay, so let's look at the carry flag first. The carry flag, which is CY, that's the flag here at the most significant bit of the program status word register, Psw register. So the most significant bit would be the CY flag. Now, I'm going to copy two values into two different registers. The first one is register A, or the accumulator. So I'm going to copy C0 hexa. In binary, that would be 1, 1, 0, 0, 0, 0, 0, 0. So that is copied into register A. And in register R0, we're going to copy 40 hexa. Translate that into binary, that would be 0, 1, 0, 0, 0, 0, 0, 0. And the next thing we're going to do is we're going to add the contents of R0, which is this binary number here, to the contents of register A, which is this content here. So let's look at the addition. So 0 at 0 would be a 0, 0 at 0 would be 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 0, and 1 at 1 in binary, that would be 0 with a 1 carry forward. And here we have 1 add 1 would be 0 and a 1 add another 0, which is this one here, and the result is still 0 with generating an extra bit, which is a 1, and this will then set the CY flag to a 1. Now this result here of the due to the addition will now replace the contents of register A. So we should see in register A, after the addition, 00 hexa, which translate into binary, which is 8 zeros. And here's the code for the demonstration. So we're going to copy C0 hexa into register A, and copy 40 hexa into register R0, and then add the contents of R0 to the contents of A. Result will be stored in A, and we should see the CY flag set to a 1 after this instruction is executed. So let's look at the demonstration. Okay, we are here in the EdSim51. I've uploaded the program and assembled it. So I'm now ready to step through the program. So first instruction is move A hash C0 hexa. So that will copy the value C0 into the accumulator. So we watch out for this accumulator here. So step it. Yes, C0 hexa is copied into the accumulator. Next we execute this instruction here. Move 0, hash 40H. So we copy this 40 hexa into R0, which is this register here. So step it. Yes, it's 40 hexa is copied into R0. Now the next instruction will copy the contents of R0 to the contents of accumulator, and the accumulator will store the result of the addition, and we should see the result. Everything is 0 with a carry 1. So let's step it. Yes, result is 00 hexa, and the CY flag, the carry flag, is set. Okay, next up is the auxiliary carry flag, AC, and that is this bit here in the Psw register. So I'm going to copy, again I'm going to make use of register A and register R0, and I'm going to copy 08 hexa into A, translate that to binary. That would be 0 0 0 0 for the 0 here, and 1 0 0 0, which is the 8. Now in R0 I'm going to copy also a 08 hexa, so the binary equivalent would be this. This would be identical to A, and the next thing we want to do is to add the contents of R0 to the contents of A. So let's look at the addition. So the 0 at 0 will be 0, 0 at 0 is 0, 0 at 0 is 0. Okay, now watch this part here. So 1 at 1 would be 0 with a 1 carry forward. Now the moment when there is a carry from bit 3 to bit 4, as is in this case, the AC flag will be set to a 1. The moment when there's a carry from bit 3 to bit 4, as is happening here, the AC flag will be set to a 1. So let's just finish off the addition. So 0 at 1 will be a 1, 1 at 0 is a 1, and the rest of these 3 bits will be 0. Now this result due to the addition, which is 10 hexa, will be stored into the accumulator. So the previous value will be erased and will be replaced by this new value here due to the operation, the addition operation. So having completed the addition, this is the result in A. And here's the code for the demonstration. So we're going to copy 08 hexa into A, copy 08 hexa into R0, and add the contents of R0, the contents of A, replacing the result, replacing the original value that was stored in A. And the auxiliary flag, which is the AC flag, will be set to a 1. So let's take a look at the demonstration. Okay, so I've uploaded the program, assembled it, ready to step through the program. So first instruction, copy 08 hexa into accumulator. So let's execute that. Yes, we have 08 hexa in the accumulator. Next one, we copy the hex value 08 into R0. So we've got 08 in R0. The next instruction is to add the contents of R0 to the contents of the accumulator. And we should have a binary result of 0, 0, 0, 0, 1, 0, 0, 0, 0. That would be in the accumulator. Let's step it. Yeah, so it's 1, 0. That's the hex equivalent of this binary number here. That's the result of the addition. And because there is a carry over from bit 3 to bit 4, the auxiliary flag is set. All right, there's a carry over from bit 3 to bit 4, and that triggers the auxiliary flag, the AC flag here. Okay, so now let's look at the overflow flag, the 0V, which is this bit here in the program status word. All right, so now let's put some numbers into register A. I'm going to copy this hex value 60H into A, and 60 hexa, the equivalent in decimal is 96 in decimal. The binary version of this is 0, 1, 1, 0, 0, 0, 0, 0. And in register R0, I'm going to copy the value 46 hexa. The equivalent in decimal would be 70. The binary equivalent would be 0, 1, 0, 0, 0, 1, 1, 0. Okay, so let's add these two numbers up in binary. So 0 at 0 is 0, 0 at a 1 is a 1, 0 at a 1 is a 1, 0 at 0 is a 0, 0 at 0 is a 0, 1 at 0 is a 1, 1 at 1 is a 0, carry 1 forward, and if you add 0 to a 1, that's a 1, and 1 at 0 is a 1. So that is the result of this binary addition of these two numbers. We are going to ignore this one. That's not counted here. So this accumulator will be replaced by this result. All right, so let's have a look. Okay, before we go any further, let's add 96 to 970. That should give us 166. The better in mind. So in register A, like I said, the result of the addition will replace the original value. So that is actually this, but if we translate that in hexa, that would be A6 hexa, and we get a minus 90. Why? Because this bit here is negative 2 to the power of 7, which gives us negative 128. And so if you add negative 128 to a 30 plus 32 plus a 4 plus a 5, you will get minus 90. Now, if you look at the decimal values, 96 at 70, we should be getting 166. But because in a sign mode, in a sign binary system, that turns out to be minus 90, and that shouldn't be, because the answer should be 166. So a negative sum of positive operand is an overflow, and you get an overflow because you're not getting this value, you're getting this. So that would trigger the overflow flag. Now the other thing to notice is that there is a change in bit from 6 to 7. Alright, that is another indicator that an overflow has occurred. Now, before I go to visit another flag, just a reminder, this is it's all about how you interpret these values here. If in an unsigned notation, this is not an issue, right? You get you get positive 1. You get a 166. But in a signed notation, this becomes negative 90, and that is actually an overflow, because you can't have two positive numbers resulting in a negative value. All right, so let's move on to the next bit. Okay, we're back in the EdSim51. I've uploaded the code, assembled it, ready to execute the first instruction. So first instruction is copy 60 hexa into the accumulator, which is this register here. So yes, it's copy 60 into the accumulator. Next instruction, copy 46 hexa into R0, which is this register here. Yes, it's copied the value 46 hexa into R0. Now the next instruction basically will add the contents of R0 to the contents of accumulator. Result will be stored in the accumulator. Yeah, and the result A6 appears in the accumulator, and the overflow flag is set to a 1, indicating the resultant addition is a negative result. Okay, so now let's look at these two bits here, RS1 and RS0. In my previous video on memory organization, I have mistakenly labeled this as RS2. So in this video, I just want to set the record straight that it should be RS0. And these two bits, RS1 and RS0, is used to select the register bank in the internal memory. So before we get into discussion about RS1 and RS0, let's remind ourselves about the internal RAM organization. This is the lower 128 bytes. So this is bank 0, and it consists of 8 registers, which is labeled R0 to R7. And each of these registers has a unique address. For example, R0 is 00 hexa, R1 is 01 hexa, and so on. Now for bank 1, which is also the stack, and you notice the is repeating R0 to R7. However, if you observe, R0 in bank 1, the address is 08 hexa, whereas R0 in bank 0, the address is 00 hexa. So similarly for bank 2, you have another 8 registers, but the addresses of these registers are different from the rest. And finally, bank 3, again, you have 8 registers, R0 to R7. Again, if you observe, the addresses are all different from the other 3 banks. Okay, so let's see how we do the bank selection. If RS1 and RS0, they are both 0, you will select bank 0. By the way, by default, bank 0 is selected when you power on. So if you want to select bank 1 here, you need to have 0 for RS1, or 1 for RS0. That will select bank 1. If you want to select bank 2, then RS1 is 1, RS0 is 0. That will select bank 2. For bank 3, both RS1 and RS0, they are 1. That will select bank 3. Here is the code to demonstrate on how to switch from one bank to from one register bank to another register bank. To explain this code, it's best to go over to the demonstration. Okay, so before we look at the demonstration, let's remind ourselves of the EdSim51, and we'll focus on this EdSim51 portion, especially on the data memory section. And we just have to remind ourselves that this data memory, or the internal RAM, the register bank, so this portion here from 0 to 7 hexa, the location, this is register 0. When you first power on the EdSim51, it's default to this register bank. And so this would be R0, R1, R2, R3, R4, R5, R6, and R7. So these are the registers in bank 0. And these are the registers in bank 1. Alright, so this will be, so in bank 1, this would be R0, R1, R2, all the way to R7. And this will be bank 2. And last but not least, this is register bank 3. Okay, so now we are in EdSim51. I've uploaded the code and assembled it, and it's ready to step through the program. So the first instruction copies this value 00 hexa into register 0. It's already 00, but we'll step through that. So, and then the next instruction copies 11 hexa to R1. So watch R1. And it appears also here because this is R1, this is R0, this is R1. And the next one, 22 hexa, will be copied into R2. And you should see R22 appearing here too in the data memory. So yes, R2 here, 22 here and 22 here. The next, we'll call the subroutine switch, and we will get down to this part of the code. Yes, it's here, and this instruction will clear RS0 in the PSW, which is this bit here. Again, is already set to a 0, but now mine will step through that. And the next one will set RS1, which is this bit here, you will see that a 1 appearing here. Yes, it does. What this means is we now switch to bank 2 of register bank 2, which is this portion here, and watch as I copy this value A0 hexa into R0. It's R0 here, but it's in register bank 2. Alright, so R0 in bank 2. The next one copies B0 hexa into R1, and it's here B0 in R1 in bank 2. Next one C0 into R2, and it's appearing here C0. Next thing, it will clear both RS0 and RS1, which is these 2 bits here. Remember, these 2 bits will select the register bank. So step it through, so both of them now 0, 0. Now we're back into bank 0. We'll see that in a minute. Now it will return back to the main program, which is this part here. Yes. Now we copy 4 hexa into R0. And watch this bit, this location here, which is in bank 0. Watch. Yes. So it's R0 in, 4 in R0, but it's in bank 0. Next one is 5 into R, copy 5 into R1, and 5 is appearing here, and then finally 6 hexa into R2, and it's in R2 in bank 0, and we'll jump to the stop, and we're done with the register bank. Okay, so we've come to the user flag, which is the F0 flag, and that is this bit here in the Psw register. Now to set this bit, the F0 flag to a 1, you could use this instruction, set B F0, that would set this bit to a 1. And if you use CLR F0, that will set this bit to 0, or we say clear the bit here. And the demonstration code is pretty straightforward. We use set B F0, that would put F0 to a 1, and CLR F0, that would put F0 to a 0. Let's take a look at the demonstration code. Okay, so we'll take a look at the code, the demonstration for the user flag. So I've uploaded the code, assembled it, ready to step through it. So first instruction is set B F0. F0 is this bit here. Alright, so watch it, this bit here, so step it. Yes, it's set to a 1. This is the only bit in the Psw register that the user can write to it. So now the next instruction will clear this bit. CLR F0 will clear this bit. Yes, it does, and it's clear. Okay, so we now come to the parity flag, which is the P flag, and it's this bit, the least significant bit in the Psw register. Now the P flag will be set when the number of 1s in the accumulator is odd number. This only applies to the register A or accumulator. It doesn't work for any other register. So if we copy 2A hexa into the accumulator, the binary of 2A hexa would be 0, 0, 1, 0, 1, 0, 1, 0. And if you count the number of ones, there are 3, so this is odd number, and so the P flag will be set to a 1. Let's take a look at another value. This time we're going to put 28 hexa. In binary, that would be 0, 0, 1, 0, 1, 0, 0, 0. And the number of ones in the accumulator now is even. So the P flag will be set to a 0. So here's the code for it, for demonstration. So we're going to copy this value into the accumulator. Once we do that, the number of ones here is odd. The P flag will be 1, equals to 1. And if we then copy this 28 hexa into A, the binary equivalent is here, and you can see it's even. So the P flag will be set to a 0. Let's take a look at the demonstration. Okay, so I've uploaded the code and assembled it. Now we step through the code. So we are now looking at the P flag, the parity flag, which is this bit, the least significant bit in the PSW. And just to remind ourselves, this will be set to a 1 if the number of ones in the accumulator is odd. That means that odd number of ones in the accumulator, P1, will be set to a 1. Unfortunately, we won't be able to see the binary, but we should see P set to a 1 with this value 2A hexa. So let's step it through and watch the accumulator and the P flag here. Yeah, it's set to a 1 because the number of ones is even in the accumulator. The next instruction will load this value 28 hexa into the accumulator, and the number of ones will be even, so P flag will be set to 0. Yes, it's set to 0. Now just to clarify something, the P flag is only affected by the contents of the accumulator. It does not get affected by any of these registers. So to demonstrate that, I'm going to copy 2A hexa as in the first instruction. In the first instruction, when I copy that into A, the P flag is set to 1. So now I'm copying the same value into R1, and let's see, it shouldn't affect the P flag. Yes, it's copied 2A into R1, and the P flag is not affected. Okay, so we've come to the end of this video, and as usual, I've provided a link to my code that I've used in this video in the description below. And so thank you for watching, and hope to see you in the next video. Bye.